Is that okay with you, Xudong?
Yes, yes, sure. I think the goal here is to apply what we learned on the sun regarding the CME generation mechanism to other cool stars. By cool stars, we mean sun-like stars, spectral type G, and stars of lower masses, K and M dwarfs. And those stars, we believe, operating with a similar dynamo and generating the magnetic fields in a similar way. So most of these eruption processes are magnetically driven. All right. So here's an outline. So the talk will mostly be a review of the literature about how why this problem is interesting and what we know about the stellar eruptions. So the work that I'm going to show of my own will be towards the end, and it's basically a simple calculation that gives you a sense of what is different on other cool stars compared to the sun, and why we are observing fewer CMEs. Okay. So to start, I will introduce the motivation of this work, the so-called missing stellar CME conundrum. Okay. And then I will talk about a proposal, how we could use what we learned from the sun to address the so-called missing stellar CME conundrum, which is the suppression of the Torus instability. Then I'll introduce the model, okay, which introduced the concept of a so-called Torus stable zone on cool stars. And then some detailed calculation and conclusion. So as you all know, flares and CMEs are a magnetic phenomena on our sun. And the right is a famous cartoon from Martins and Quinn, 1989, that shows the magnetic fields in a 2D picture. So they are rooted in this dense layer of solar photosphere, and in the corona, if they are somehow energized, they would form this so-called magnetic flux rope. And if the energy and helicity accumulates to a state that they are no longer stable, the reconnection will occur and sort of sever the top part, the flexible part, from the closed loops. So they would get ejected into the interplanetary space by a Lorentz force. And the flare and CME are two aspects of this same process. By that, I mean that the CME is a consequence of this ejection. That refers to the top part that's actually flying off. And flare is another consequence that is from the reconnection, which accelerates particles, which gets then thermalized in the lower layers and heats the lower coronal loops. That's the E&M emission part. Now, the onset mechanism for this whole process, for the ejection of the CME, can be broadly classified into two groups. One is the so-called ideal instability that does not directly involve the magnetic reconnection at first. And the other type is magnetic reconnection driven. Okay. And on a larger scheme, CME arguably have larger impacts on planet habitability, on the Earth and exoplanets as well, compared to the flares, because these magnetized plasma directly impacts the magnetosphere of planets. On the sun, okay, the flares and CMEs are intricately connected in the sense that whenever there is a large flare, by large I mean X class and above, there usually is a CME related. So on the right is a statistical survey of the correlation, okay, of between CME and flare. So this the y-axis is the CME association rate, and x-axis is the peak soft X-ray flux. So I think X-ray is somewhere here, 10 to the -3. So by X1 or X3, this association rate is 100% almost. And this is the total flare emission, okay, similar distribution. But of course, there are exceptions to this. Okay, the famous one is the 2014 12192 active region, which is the largest spot group since 1990. It produced 6 X-class flares during its disk transit, but none of them was associated with a CME. All right. So this is the general rule, and there are exceptions. So what happens in this special active region? One argument is that there is a so-called failed eruption. So there is a CME or flux rope formed in this active region, which wanted to get out. However, for some reason, it didn't. Okay. So this is the so-called failed eruption that sort of explains why we get a large flare without a CME. Now, if we look away from the sun and look into the dark side on cool stars, late-type stars, thanks to the recent surveys, optical surveys, like Kepler and TESS, we are finding thousands of so-called super flares on G, K, and M types of stars. And if we estimate their bolometric flare emission, these super flares will have the energy output on the order of 10 to the 34 to 10 to the 36 ergs. Recall that for the X-class flares on the sun, the emission is on the order of 10 to the 32 ergs. So this is 100 to 10,000 times more energetic. Now, because these G, K, and M stars are mostly magnetic, I'll talk about their magnetic fields in a minute. So at this moment, I think there is a general consensus that these flares are magnetically driven in a similar fashion as on the sun. Okay, and there are observational evidence supporting that. For example, if you survey the flaring stars, you will see that strong flares often occur on stars that rotate faster, have larger spots, both of which are evidence that the star has a stronger magnetic field. Now, if you apply the solar CME flare association rate to these stars, so you would expect to see also thousands of stellar CMEs, right? But in fact, CME detection from observations are quite rare. So up to now, there are only about 40 or so candidates through several different mechanisms. For example, Doppler shifts of the Balmer lines, X-ray absorption, and EUV or X-ray dimming. Let me explain how people do that. Okay. So on the right-hand side is, in my view, one of the best case scenario of Doppler shift detection method. So here, okay, the Japanese group, they observed a nearby dwarf star and looked at the H alpha line. Okay, so this is a stack plot of the H alpha line. So x-axis is time, y-axis is the wavelength, and each column is a background subtracted, pre-flare state subtracted H alpha spectrum, right? So before the flare, basically it's just noise, right? After you subtract the background, the pre-flare state. But once you start to, the flare starts, okay, the red and blue color here indicates emission and absorption, okay. They don't mean Doppler actually. So it's confusing. But in order to see the Doppler, you need to see if the signal is above or below this dotted line, because this dotted line is the nominal line center. So if it's below this dotted line, the wavelengths are longer, so it's redshifted, okay? And if it's above this line, the wavelengths are shorter, so it's blue shifted. So in the beginning, you will see this blip of redshift in emission, which were interpreted as flare, the chromospheric condensation, right? So you have a downward push of the spectral line, okay? So this is actually observed on the sun as well. But then you see a large blue shift, a few minutes, tens of minutes after this initial brightening of the flare. You get a absorption, okay? and which is also highly blue shifted. I think the speed at this time is about 500 kilometers per second. That exceeds the escape speed of this particular star. And what's more interesting is that from this initial large velocity, the velocity gradually decreases, okay? And the slope indicates the acceleration, right? It's the time derivative of the speed. So if it's this slope, it means this means the gravity deceleration, right? So it seems that this ejecta, if you can interpret as this cartoon shows, you have a CME launching towards you with a cool material entrenched so that H alpha is in absorption. You initially get a quite fast speed as on the sun, the CME is ejected to a high speed very quickly, right? And it appears that the CME is gradually slowing down by some mechanism, either through gravity or magnetic tension, right? So this is one of the several mechanism or method you can infer that there might be ejection occurring on stars. Of course, there's currently no hope to resolve these stellar CME ejection. So we will have to rely on these indirect measurements, such as these spectroscopic observations. But I think this is really impressive, the absorption and deceleration here. Now, what does this particular Doppler method look like on the sun? It turns out it's not that easy to detect Doppler velocity on the sun. People have tried to use Eve data, but usually what they got is a quite slow speed, around 100 kilometers per second. Okay, that is probably not the CME, but rather the upflow in the low atmosphere. So this is the recent paper. I think this is one of the first examples that I'm aware that shows a high-speed upflow using Eve full sun integrated spectral line. So this is a recent X-class flare last year, October, and the authors looked at a series of oxygen lines, I think, that is at sub-million Kelvin temperature. And this active region is right at this center. So whatever you get will be the true Doppler speed, more or less. Right? And here's the spectral line, okay, stacked, okay, with some offset. And then the time goes from bottom to top. So then you see the spectral line here, right? It's quite blue shifted with a speed of 500 kilometers per second. If you take a closer look at the spectral line, you can see a more or less stationary component, and then you have a blue shifted component of 400 kilometers per second. Okay. So this is, I think it's a pretty clear case. The difficulty here is that you will need to make sure that the signal is actually coming from the ejector rather than the background or the flare loops. And that is not particularly easy because once the CME is launched, it expands very quickly, so your density drops really fast. Your emission actually gets weaker and weaker, and also the plasma cools as it expands. So it's not very easy to detect these things. On the stars, okay, the ones that I just showed you is an absorption feature from the H alpha line. Here is another example from the hotter corona line observed by Chandra. This is a line that is formed at about 25 million Kelvin. Okay, so it's a pretty hot corona line, and of course, being X-ray from a cool star, you don't have many counts. So this is a count rate per kilosecond. Okay, so 1,000 seconds they get maybe 4 to 7 photons. Right, there's very few of them. However, if you believe this measurement and you look at the spectra, after you integrate over like a few hours, you will get a blue shifted component here as well. Right, this the initial states. This red color is actually blue shifted. So I don't know why they use this color. But okay, you get a velocity of about 200 to 300 kilometers per second if you just gather all 20 photons and plot them as a spectral line, right? You get a several hundred kilometers per second. So they interpret this as a signature of the stellar CME from the spectral line directly. Okay.
Can you see the stellar CME and not the solar one? Is it because the flare is so much stronger on the stellar?
I
mean, I know it's hard to move on 1 pixel, but I'm just.
I don't know the answer, but if you think about a very hot line, for example, over 10 million Kelvin, the AI, for example, 95 or 131 angstrom, right? All the hot emission will be coming from the flare region, so they will be dominated by the flare region, right? So it can resolve that. So it's not actually from the large body of CME. The CME itself is not that hot, right? But then if your CME is about million Kelvin, then it's dominated by the star itself, right? Because most of the plasma, most of the emission measure from the sun is within that 1 million range. So if you have a small Doppler shifted component, you might not be able to see it, just because the background, is so strong. I don't know. This is just my guess. I haven't looked at data myself.
In the previous slide, you showed the results of H alpha.
Mm-hmm.
So do you think, similar, if we observe the sun as just one pixel, I think, we can observe any signals of CME.
The authors did that with their own telescope. They looked at the small eruption, smaller flare. If they integrate over just the active region, you get a similar pattern. I don't know if you integrate over the whole sun, you are able to see that, because the background would vary a lot, because there are other H alpha regions, right? But in that paper, the authors showed 2 examples from a active region integrated spectra, H alpha spectra. There you see a similar structure. Presumably, because in these smaller stars, these magnetic field is stronger, so the filament are expected to be large, so the contrast is actually larger, so it might be easier to see. But the thing is that here, what you see if you use the solar analog is the cool entrenched filament or prominence, rather than the CME itself, right? Because you're seeing the absorption feature. And here you can argue that it might be from the CME body itself, because it's emitting in 0.5, 0.6 million Kelvin. Anyways, another method that is more promising is the stellar coronal dimming. Okay, so on the left is the solar case looking at several EUV lines. Okay, so this is one of the reasons we don't see the Doppler. It's very difficult to see the Doppler, probably because there's huge amount of dimming here. That is a few percent of the original full sun brightness, right? A large blob is just evacuated from the sun. But on the sun, when you actually do a survey of all the eruptive versus non-eruptive flares, the one persistently successful feature is the dimming. Okay, so dimming is a very good way to separate flares with and without a CME. So whenever you have a flare with CME, you see dimming. So if you have a flare without a CME, you don't see a dimming. So this is the best indicator of a CME on the sun. So this group from Austria actually looked at soft X-ray and EUV archival data from a group of stars, and I think they found about 20 or so cases where you see these kind of dimming right here after a large flare. So they conclude that this can be a candidate of stellar CME.
So what observations can you use for this? For the sun, we have so many spacecraft.
Right.
For the dark side.
They have back then they have I think called the EUVE, which is a EUV instrument, and then they have a soft X-ray, because for these cooler stars the magnetic field is stronger, so the coronal temperature is hotter. You actually the most common plasma is actually emitting in a soft X-ray temperature, hotter than the sun. So you can use Chandra, for example, to observe those.
So, George, I have a question for you.
Uh-huh.
What about still CMEs? Is dimming a good indicator for them?
Stealth CME, okay, so I think the survey here, what the Hara group did, uses a flare as a selection of the events. So they only considered when you see a flare, whether or not you see a CME. So stealth CME on the sun usually doesn't produce a strong flare signal. That's probably not included in their sample. But I guess you're right that you might not be able to see a strong dimming signature, and that is probably going to be missed in stellar CME because there's just no way to see them. Anyways, what I'm trying to get at is that we have ways to detect stellar CME, although they're more difficult than stellar flares, right? But still, you would expect to see some, if not, for each large flare. But still, we are not seeing, many, very few actually. So in my view, it's probably not a observational bias. We are actually getting fewer stellar CME compared to the sun. So actually, this is the assumption that I'm going to make, right? Otherwise, the work where we're doing next is meaningless because it's just a detection bias, right? So this so-called missing stellar CME conundrum, to my knowledge, people have done bits and pieces, but I think it was proposed more in a coherent fashion in this past decade. And here's a diagram of statistics of the flare X-ray energy and the CME property on the sun and other stars, okay? So on the top, okay, so the x-axis is the X-ray energy and y-axis is the CME mass. And all these dark points are the solar values, okay? I think they use one of the CME catalog, and you can use Gauss X-ray. And then if you extrapolate this this blob, okay, and you plot the a dozen or so cases people have detected on other stars, if you make lots of assumptions, you can estimate their mass of the CME mass, right? They more or less lie on the same trend line, okay? So mass-wise, people believe that the stellar CME is consistent with the solar scaling. However, if you estimate also their kinetic energy, okay, now all these stellar cases lie below this trend line, right below trend line, which means their velocity is relatively low compared to the solar case, right? So what this means is that for stellar CMEs, either the stellar CME does not get out at all, or if they get out, the speed is lower. Okay, so that if you believe the data, so this is sort of their conclusion, okay. So there might be something going on other stars that is slowing down these CMEs to the point that many of them don't actually get out. And if they get out, they're quite slow, okay. And there are other observations consistent with that. For example, once people get interested in this this phenomena, they are recently starting to do these optical radio campaign of nearby flaring stars. So if you have a fast CME like on the sun, you're expecting to get type 2 radio bursts from the CME shock. So they spent tens of hours monitoring nearby stars, and they've seen a few large flares. However, no type 2 radio burst at all. So that's another line of evidence, okay. So this is what I meant by missing stellar CME conundrum. And this is important because it will have major implications on the mass and angular momentum loss on these stars, which will affect their stellar evolution spin down. And also it will largely change, how the stellar activity affect the exoplanetary habitability. That's why I think it's important in the astrobiology context. Now, coming back to the sun, now it's the part that actually related to what I'm doing. that we think, okay, this missing CME conundrum is probably related to the different magnetic fields on stars. And this paper, Jeremy Drake proposed that active region 12192, the one that I just mentioned on our sun, which produces many CME-less flares, could serve as a solar analog for these CME-less flares. Okay, I got interested in this project first because I noticed that these stellar papers were citing the work that I did on this particular active region, so I sort of got interested in that. Now, after they proposed, this guy, Julian Alvarado Gomez, who worked at CFA as a postdoc, did a series of MHD simulations where they place this Gibson-Low type of magnetic flux rope in a background dipole field. And I think it was the Michigan model to see what happens. Okay. So on the right-hand side is the result. The x-axis refers to the amount of colloidal flux, the twist they put into this flux rope. And the x-axis is the CME kinetic energy they get. And these dots, each dot shows a CME run, and the difference between these dots are the overlying, the dipole field they impose on the CME simulation. So from left to right, basically, what do I mean? Okay, so yes. Okay, no, actually, they put in a strong dipole, excuse me. What happens is that they put in a strong dipole field, which is 75 Gauss, I think. What actually changes is a different colloidal flux they put into the flux rope, actually, right?
What does that mean, a strong dipole field? I mean...
polar field, you can think of that, yeah. The large scale.
Like across the whole star?
Yes, yes, yeah.
Okay,
yeah.
not just, okay, the
yes.
entire star.
It's entire star, yes. Global.
Confining.
Yeah, yeah.
That's what you're thinking?
Yeah, yeah,
Okay.
yeah. So on the sun, okay, the global dipole is like a few Gauss, so that does not do much on active region scale, right? What they believe is on the stars, these large global fields can do something to the eruption. So that's one difference between the stars and the sun. So if they put in this 75 Gauss dipole and then they vary the colloidal flux, what they found is that up to 10 to the 32 Maxwell of colloidal flux, any flux rope below that threshold, you will not get an erupting flux rope. So you will have the flux rope going because in this model, the flux rope is out of equilibrium to begin with, but they don't make it out. They are confined by the overlying large-scale field. Only when you get to this 10 to the 22, if you keep injecting energy to the flux rope, it will make it out, right? And if you look at this look and use some other empirical scaling, you will find out that this kind of magnetic energy in the flux rope corresponds to the Carrington level event. What this means is that on this star with a 75 Gauss dipole, only when you get a Carrington level event can you produce a CME. Anything below that, it will be confined. So that's the effect of a 75 Gauss dipole. So this is sort of a demonstration of what the dipole field can do to your eruption. And that sort of demonstrate that, if you have a stronger dipole field, you can actually limit the CME, number of CME you get out, right?
What is the 775 AD event?
That's an even stronger, believed to be an even stronger solar event because they saw a large number of energetic particles in the tree rings. I think that's from the tree rings isotope, they inferred that there was probably a energetic particle event that is 1 order of magnitude stronger than the Carrington level event.
Japan, I think.
Precise as 1 year,
Well, tree rings, yeah. You can actually be precise. Really, really close.
The ice core?
So what is the between?
Yeah, that's a good question. It depends on the orientation. I don't know the details, but it will make a difference, I believe. Yeah.
And I mean, in principle, it doesn't have to be a dipole global. It could be any overlying
Yeah,
confining field, right?
yeah,
So if you had big sunspots and little sunspots that were, hemispheric in size, any kind of overlying field could do it.
That's what I'm going to actually run for from my work.
We haven't gotten to your work yet.
Sorry.
No, that's good.
So that's what I'm saying, that most of its introduction is set up. The actual work, my actual work is actually a little, a few plots. Okay, I'll be quick. So, but now we start to the proposal of why we're doing this. So what we are getting at our work with Tibor and Mark is that we're going to test whether torus instability play a role in this confinement. Okay, we put a theory to that. So you have sort of theoretical argument to this. So I'll go quickly. Torus instability is basically a mechanism where your overlying field strength decreases slowly with height. Then it's very difficult for the CME to erupt. Okay, so here's a comparison of two flux ropes. Same flux rope with different overlying field. The bottom one has a stronger overlying field, and top one has a weaker one. So the top one erupts. And what describes this overlying field is the so-called background field decay index, which is the slope of your background profile as a function of height. Okay, so if your background decay is slower than height to the minus 1.5, then that means it's a strong background field, and it's very difficult for the CME to get out. So at that case, torus instability is unlikely to occur, right? But what I'm trying to get here is the new concept, not quite new, but a concept that I want to emphasize on is the torus stable zone, okay? So whenever you're below that critical height where your decay index reaches this threshold, anything below that particular critical height, you're safe. You don't get any eruption, right? But once you get above that critical height, CME can occur. So now you can compute these torus stable zone with different magnetic configuration. If your torus stable zone or the safe zone is very large, so most of the magnetic activity happens within your torus stable zone, then there will probably be no CME. Otherwise, if you have a very tiny torus stable zone, in that case, whenever you get a disturbance of a flux rope and it gets out of the safe zone, it will just go. So the size of this torus stable zone will give you a sense of how stable the coronal structure is. Okay, I might want to skip this. So what this slide basically shows that it works on the sun. Okay, if you compare flares with and without CME, you will find that for flares without a CME, the so-called confined flare, the height of the critical height or the size of your torus stable zone is large. Okay, so active region stays within that safe zone. And in comparison, if you have an eruptive flare, the stable zone, the safe zone or torus stable zone is relatively small, right? So it's very easy for the active region to get out of that safe zone.
What's the blue histogram? Yeah, that's the other thing.
The green one's a total.
Oh, that's a green.
Yeah, green one's a total. Blue and red. The difference is blue and red, and this critical height tells you how big the torus stable zone is, basically. So for the red one, confined flare, the distribution is towards right. That means your critical height is larger. Okay. Okay, now if you apply this to other stars, there are two ways of a extended torus stable zone can explain the lack of CME. So in the first way, okay, in the extended torus stable zone, okay, a leading mechanism for solar CME, which is torus instability, will not occur actually. So that basically limits the way you can trigger a CME, right? You will have to use some other mechanism to trigger the CME. But that limits the number of your CME eruption. And mode 2 is something we found quite interesting in our own work, and I will talk about in a second. Okay, I'm going to skip it from right here. Okay, so this is actually our work. Okay, now I'm going to describe what we did. So what we did is quite simple. Because there are just so many degrees of freedom when it comes to describing a stellar magnetic field. So what we are trying to do here is really simplify it and test the most basic and simple configuration. And that is a global dipole plus a bipole, which acts as a stellar active region, just two components, right? And we're going to test the most simple case in the sense that your star spots or the active region is aligned with a dipole, completely aligned, right? So that gives you the strongest confinement possible because your overlying field from the dipole and the active region are well aligned. So that gives you the upper limit of how strong this confinement is. So everything is simple, and we're going to use a simple potential field surface model to do that. Okay. And the surface bipole, we use a analytical function that is proposed by Anthony Yates, which is a fit of the solar active regions of cycle 2024. Yes. So when everything is simplified, we have three free parameters. Okay. One is the star spot or the bipole size. That is the separation between the center of these two bipoles. And the strongest magnetic field, I'm fixing it at 3,000 Gauss. Okay. So basically, the spot is fully characterized by this the bipole size. And then the second free parameter is the global dipole field strength. I'm varying it between 0 to 1,000 Gauss. This is based on spectral polarization observations from cool stars. Many of the M dwarfs can have dipole as strong as several thousand Gauss. And the third is the source surface radius. For the sun, we usually take it to be maybe 1.5, 2.5, up to 4. But there are evidence that for younger stars, it's larger. So I'm varying it between 2 and 20. Okay. So basically, you have three parameters. Then you can calculate a grid of models. And for each model, you find what this critical height is and see how that is different for other stars compared to the sun. So it's really simple calculation. Okay, before I actually show the final result, I'd like to discuss a little bit of the free parameters, okay, how that is different on other stars compared to the sun. So the first free parameter is the star spot size, okay. So on cool stars, the star spot can get really, really large. On some of the stars, if you look at their brightness modulation, you will infer that maybe half or like 80% of the stars is occupied by star spots, right? And this is a scaling that is proposed by Guillaume Lanier. What he used his MHD simulation to show that in order to produce a flare with the energy of 10 to the 36, you need a spot that looks like this, compared to the sun, which looks like this. Right?
Wait, which one is this one?
This one, tiny one.
Tiny one.
This is X-class flare, yes. You need this one. But if you need to super flare, you need this one. So it's really, really different regime, actually, compared to what we're talking about. And this is a paragraph I really enjoyed from the review paper from Stressmeyer. Okay, so for the largest spots, that is 60 times the extension of the largest ever observed sunspot group. Because of the sunspot-like Wilson depression, the star that would make the star look like a logo of a well-known computer company, which is Apple, right? If you have a Wilson depression, the surface will become lower, and then if the spot is so large, it will look like a Apple. But what I'm trying to get at is that the star spots can be really large, and magnetic field strength, actually, people believe is similar to the sun, a few thousand Gauss. Okay. So one way to measure the star spots is to use the light curve modulation, and in here is actually a transit method. So here's the exoplanet transit. You see this curve, but at the bottom of the transit, you see these wiggles. So this is interpreted as the transit is actually, going above the star spots. So it's covering a darker region of the stars that actually induce this wiggles, okay? So from these wiggles, you can sort of model how big your star spot is. And the other way is that you can use the Zeeman-Doppler imaging technique to produce a low resolution intensity and magnetic field maps. So in this particular map that we view a star almost pole on, what they get is that they see a dark spot at the pole. Okay, so this is the intensity on the top at 3 different epochs. And then they can infer the azimuth magnetic field, which looks like a ring around this dark spot. Okay, so Sami Solanki actually proposed that this polar spot looks just like the sunspot. You have umbra in the middle, then you have a ring of twisted penumbra field that is around this polar spot. So the magnetic topology there is going to be very, very different from what we see on the sun. So that's kind of fascinating. And then you can use, again, the large-scale dipole field. You can use Zeeman-Doppler imaging to infer that, all right? But what the people find is that, okay, the magnetic field strength, okay, or dipole field is a function of how fast the star rotates. In here, parameterized as a Rossby number. So when the Rossby number is small, that means the star is rotating relatively fast, okay? And when it's large, it's rotating relatively slow, and the sun is somewhere around unity in the lower corner. So what happens is that when the stars rotate faster and faster, the magnetic field becomes stronger. So there's a power law distribution here. But once you get to a critical Rossby number about 0.1-ish, this slope changes to a relatively flat. That's the so-called saturation regime. But in any ways, relevant to this work is that there are a whole bunch of low mass stars that has a magnetic field above 1,000 Gauss. It's really, really, really strong. Okay. Skip this.
Are those a dipole field? Or
That's a good question. That's a good question. So all these measures are dipole at large scale because sunspots are dark. They don't give you photons, so you really can measure those. Yeah.
These are kind of mean fields, right?
Yeah, mean field. With the Doppler imaging, you can resolve lower orders, but you can also use unpolarized light. Just look at the split to get a mean field. So there are different ways to do this. So this is the one that I was going to skip, but if you actually do the mapping of the low order magnetic field, you can get a topology, whether it's axisymmetric, whether it's mainly poloidal or toroidal, or how strong it is. So here is the same diagram, x-axis the rotation period, y is the stellar mass, okay? And the sun is here, okay, on the upper right, the period is 27 days, right? And the stellar mass is 1, sun is here. So the magnetic field is a few Gauss, so it's a tiny, tiny symbol. Compared to the low mass stars, okay, these are the M dwarfs, they are large. And the difference is G-type stars are here, and this is K-type stars. You see a lot of stars, which means the stars, these stars have a non-axisymmetric and also toroidal field, very different from the sun. But then you move to fully convective stars, again, it becomes axisymmetric and poloidal. So, but I mean, this is not particularly relevant to what I'm going to do next. The thing that is important is that these symbols are large, so they have strong dipole, right? Thousands of Gauss.
Is that a function of the depth of the convection zone?
You would think, but okay. But the interesting thing here is that you find M dwarfs, low mass stars, both in this branch and in this branch. So that people are suspecting whether, the tachycline is important for a solar type of dynamo, because you can get a solar type of scaling in this unsaturated regime without a tachycline, actually. So it's a mess. Nobody knows what's going on, actually.
Aren't M dwarfs fully convective?
If they get below a certain mass, yes. Okay, the third parameter is the source surface height. So you can ask Mark, because the first paper I read was done by Carl and Mark about the scaling of the source surface radius, okay, to the surface magnetic flux. So their argument is that for younger and more active stars with stronger surface field, your source surface needs to be larger compared to the sun right now. in order to reproduce the evolution of the rotational speed variation. So I'm not going to get into that, but the gist is that for more active stars, you need a larger source surface radius. All right, finally to my results. Okay. Sorry, it gets really extended. So the x-axis here is the thing that we actually, the decay index. So 1.5 is the critical number. And y-axis here is the critical height. So each curve, okay, is the decay index as a function of height for different cases. So the left-hand side is the result for a dipole-only magnetic field. There's no active region at all. So this is only a dipole. Okay, so this is what the Torus stable zone looks like. So it extends from about half the stellar radii to a full solar stellar radii. Well, as expected, okay, the higher your source surface is, the larger your Torus stable zone is. Not very interesting. The next type is that all these things you sort of expect them already, right? But I think it would be good to put a number on it. So the other case is that you don't have a dipole, you only have an active region. Okay. So what this from this diagram, you can show that this height of this Torus stable zone is exactly half the size of this active region. This is not surprising as well. People have seen that. And this is what happens on the sun usually, okay, because the constraint of this eruption is mostly from the active region itself rather than the global dipole. What's more interesting is that when you put these two together and see what happens there. So this is a more general case where you have both the global dipole and the spot magnetic field. So on the top, okay, is where you have a huge star spot of 25 degrees. So these are the big blobs, the Apple logo type of star spots. When you have that, your star spot is going to play a major role, okay? And different curves here show you different dipole, global dipole value. And the global dipole value does not change the height very much because the star spot is so large, it dominates what happens, right? It's not very interesting. What's more interesting is that when you have these smaller spots, like on the sun, about 5 degrees, now when you get at no global dipole, when you add 10 Gauss dipole, 100 Gauss dipole, and 1,000 Gauss dipole, the profile gets very, very different now, okay? So in the beginning, it's just what the active region is, and it's relatively low. But once you get to about 100 Gauss, what happens is that the curve is sort of pushed down, and then you get a Torus stable zone right here in the lowest corona. Then in this region, right, the global magnetic field, the overlying magnetic field from the active region is weak enough, but the dipole hasn't kicked in. And when you get a little bit higher, this is when the global dipole kicks in and then push the profile again below the critical value. So you get a secondary so-called safe zone stacked on top of the regular one, right? So this is something new. We've never seen it on the sun because we don't have that strong global dipole. So this is the new mode that I was talking about. So on a star, when you have a solar-like active region and when you have about 1,000 Gauss global dipole, what could happen is that you have an eruptive flare as you would do on the sun. But when it erupts, it will get hit by a secondary safety zone, and that eruption might get stopped. So that's a new mode that might, stop the CME from going if you are on a star with the solar type active region and 100 Gauss dipole. And of course, when you increase your global dipole to 1,000, you can see this safety zone approaches 0.6 stellar radii, okay, and normal active region size will never reach that. So basically, once you get to 1,000 Gauss, it's very hard for active region to produce any CME through this Torus stable mechanism. Okay, so basically that's it. This diagram is basically just a summary of what I was showing with the curves. Okay, so x-axis is the active region size, y-axis is the dipole size, and our sun is limited to this very, very tiny corner, right? Everything else is unexplored. And what happens is that when you have a combination of the spot size and global dipole in this red triangle, we will get this secondary Torus stable zone. So something interesting will happen. And otherwise, if you get into this yellowish zone, the global dipole will take over, you know. And if you at the lower right, it's still the spot dominated just as the sun. The source surface radius, basically, if you have a higher source surface radius, okay, on more active stars, it would actually have a higher safety zone. So that's consistent with what we are saying. Okay, there are four slides are what we actually did. So not much calculation. I think the setup and the context is more important here, I guess. Of course, this model has lots of caveats. It's highly, you know, idealistic. Because on more active stars, you would expect active regions to emerge at higher latitudes. They are also probably going to be fragmented and more nested because you have lots of active regions emerging within each other. Okay. And also the alignment between the spot and overlying field. This is probably not realistic because I aligned the spots along the dipole at the equator, which is not very realistic if you think about it. And again, like what Georgios mentioned, that this model will not be applicable to prominence or the self-CME at all, because this only considers the strong and large active region type eruption, and that does not apply to the streamer blob type of CMEs. And of course, on the sun, there are flares without magnetic flux probe as well. So that will also not be, this model will also not be applicable because this requires there to be a flux probe to begin with. Okay. So what from here on, what we can do, okay, from the observational point of view, okay, it would be necessary to have more of these dedicated status CME monitoring campaign. Okay, they're going to be expensive, but if you want to get down to the observational wise, you have to do that. And modeling wise, one thing we could do is to use these dynamo and surface flux transport of a model to show, you know, to get a sense of what the star surface would look like. You know, this is what Carl and Mark has been doing. Okay, and I think this is Farish. I think she's a student of David Alexander.
She was.
Yeah. Okay. She did similar research, and also Duncan Mackay as well. This needs to be done. And what I am trying to do next is probably to actually put flux rope in that background field and vary the flux rope perimeter as well as the background field to see if it can actually reproduce the confinement of this active region. So this will be idealized MHD perimeter study. Okay. And also there are data constrained MHD modeling. For example, this one from Ben Lynch, where he took the ZDI map of a star and share the equator neutral line here, okay, to produce a global size of CME eruption. And Meng has also done similar, studies with ZDI and the magnetic flux rope to see what the effect of this eruption is on stars and exoplanets. These data constrained MHD will teach us something as well. All right, here's my summary. So if you want to, take home one message through all these huge amount of material, I think this is the sentence. Okay, suppression of the Torus instability may contribute to the lack of CME detection. That's it. Thank you.
There are so many questions in the chat.
Okay, let me.
I just want to point, oh, sorry.
So Shay, go ahead.
Okay, sorry, Alex and I are in the same room, but on two different devices. So we have a couple questions in the chat, but so mine is, and maybe you answered this and I just missed it, but is stellar age, does stellar age have anything to do with this? Because younger stars are more active, isn't that right? Or is it vice versa?
Yeah,
Has
yes.
age been considered in these studies?
Yes, so implicitly, people usually assume for the same star, it gets less active as it ages. So basically, here, if I'm using a larger spots or a higher source surface radius, that you could think of that as we're looking at younger stars. Sort of in an idealized sense, that's the case, yes. Does that make sense?
So what are the stars? So if we're only, I mean, maybe it's a limitation of like what stars have actually been studied, but if you look at only like stars that are about the same age and, you know, or mass or what, you know, collectively like very similar to the sun, do we see the same sort of conundrum, or are they about as active?
Okay. You're talking about observational wise, right? Observational wise, the thing is that there are only 40 events, right? There's not much statistics, at least. The CMEs they saw, I believe, the X-ray Doppler event is actually from a G-type giant, and many of them are from M dwarfs. So I don't know how the age distribution is like in the sample. Yeah, the answer is I don't know whether it's same for the conundrum is the same for solar type stars or solar age stars or younger stars, observationally.
So Georgia has,
That one was answered.
oh, that's answer, okay.
Cycle relationship.
Hello, hi Xudong. This is Meng.
Hi.
So, very nice talk. So I have a question about this confined eruption. So, can we observe that or confirm this confined eruption from the stellar observations? So, what's the best ways, in your opinion, to observing this?
Well, what we can get is integrated light curve and spectra, right? I guess you will need to look at the sun and try to do a similar study as the ISI group that looked at the dimming, right? They looked at all kinds of features for eruptive and non-eruptive flares, and they saw dimming, right? And dimming is the only indicator, at least in their sample. What other things that might be helping, I think, might be the shape of the light curve. You know, if the confined one has a different kind of light curve. But so far, I mean, it seems at least from the number of features they looked at, right? Flares without CME, the dimming seems to be the only one that is consistently doing a good job of separating the two classes. And outside that, I don't really know if there are other ones based on solar eruptions. Yeah.
So how about this late phase events observed by Eve? So I record there's some statistical studies recently that they relate a late phase eruption, late phase emissions with the confined eruption. Would this be an option to do the stellar observations of this confined events?
Well, I mean, I guess our best approach is that if it works on the sun, it may work on the other stars. But if it doesn't work on the sun, it probably is not going to work on the stars. So I guess if there's a statistical study that saying that late phase is correlated with that, I guess it is something to look at. But the thing is that we don't have a EUV instrument out there doing surveys, right? And the recent proposal was not selected from Boulder, if I recall.
That's very disappointing. But yeah,
yeah.
But you mentioned that for young stars, though the plasma is shipped to the high temperature. So we might find something in the X-ray or soft X-ray emissions.
Correct.
Shed more light on why 12192 was flare rich in CME4, or I forget your conclusion in that paper. You know, why it was like that.
That's because, I mean, that was sort of the starting point. We assume that is correct. So,
but it was basically Torus stable.
Index thing.
The overlying field is strong and
Okay.
decays really slowly. So over there are two components. This is one component. The other component is the energy of the core field, the flux rope, is really weak.
Okay.
But on stars, you can measure those, so we can only infer the overlying field.
So it didn't change anything, it just confirms it.
Yeah, right.
Extrapolated that.
Extrapolated, yes, with some new modes that are not available on the sun. Yeah.
So suppose the second Torus instability zone exists also in the sun.
Yeah.
Would be expected the circle-dependent ratio of erupted and confined.
There's actually a study of this on the sun. Okay, so here the secondary Torus stable zone is caused by the global dipole. On the sun, because this is not the global dipole is weak, so it's not going to be caused by the global field. But in multipolar field, you will have, for example, if you have a quadrupolar field, people do see these kind of the shape, but the spatial scale is really tiny. Okay, so you have a very small layer of secondary Torus stable zone. The same authors here has done some statistical study actually on the regions with and without the Torus stable. It's not going. Okay, this group, I think. Yeah, the one in Aurelio and Dongwang, they looked at these in this paper actually. They have a subsample with a quadrupolar field, and what they see is that with only a few events, right, the ones with a secondary Torus stable zone has a higher ratio of confined eruptions compared to the bipolar. But that's very small statistics, so I don't know if it's as reliable.
So if we look at the Q map you generate for optimize the whole mission data, that suppose give you the larger, even global structure of magnetic field.
Yeah.
That might have some clue to link to confined eruption.
Well, on the sun, again, I mean, I think the global field does not really matter as much just because it's so weak. If you look at the active region, the quadrupolar one with the secondary, magnetic field, at that height, it's always like relatively below 0.1 solar radii. So 100 megameter is like maybe a 0.1, 0.15. So everything's below that. So the global field for the sun at that height is very weak already. It's not going to do much. That's what my opinion, at least. But the situation, I mean, the scaling is very different for other stars, just because the field, global field is so much stronger.
Naraki, you have a question?
Yeah. This is just a kind of a old man's gripe. Old man is called the Giza, according to Greg Slater, the American colloquium. But anyway, Giza's comment is that you're dealing with torus instability, and that's the ideal process. And we know that on the sun, we don't often observe CMEs without flares. So at least some non-ideal processes are involved, right? And so then what's the relation of CMEs and flares? And when you talk about flares, we often talk about the Gauss X class, class, right? But that is kind of, to me, it's nearsighted, because the energy going into X-ray emission is just 1% or 2% of the total energy that is involved in flares. That's one comment. So maybe there are some hidden, there may be some hidden physics, which may not go with Gauss X-ray flux.
You're absolutely right. I mean, the one that I'm looking at, when we talk about torus instability, we are thinking about which comes first, I guess.
Yeah.
For these strong field regions, once there's eruption, both will happen. Now, if you have a plasma upward movement, there will be a reconnection going on. So there's always going to be these reconnection. The thing is that, for CME, which comes first? That's a sort of a tricky question, and if the chicken comes first or an egg comes first, right? So in this case, I think we're considering the triggering mechanism being the torus instability. But of course, once you start to have an eruption and reconnection, it's going to be a positive, a feedback loop. So it will make the eruption easier once you get a reconnection, right? So you're absolutely right. Both will be involved. But I guess the thing that I'm interested in here is that whether the triggering, if it assumes that's the torus instability, can occur under a certain magnetic environment.
I think that's very important. And which comes first is a really interesting question. And like Xudong had the simulations, right? And he talked about the two typical types of magnetic interaction. And one of them is reconnection first. Another one is eruption first, kind of. And and I think by looking at Lewis Harrod's results, they at the EC, they said that the corona dimming is the only signature of X plus flares that have to do with CMEs, but they are really limited to X class flares. So it's a kind of bias. So there may be lots of cases where the X-ray emission is not so great, and the CME effect is much, much larger.
Yeah. So I guess I implicitly limit myself to these large active regions. So I'm already implicitly limiting myself to the sample that Howard et al. Looking at, because I'm talking about super flares in these strong active regions already. I guess that makes my life easier, but that doesn't explain everything, because other weaker cases really don't have any observational handle at all, right? So it cannot be studied, I guess. So this is the type of things that we can study at the moment, I guess.
I completely agree. Thank you.
I think this is along the lines of what Todd was talking earlier. Did you try with orienting the active region field opposite to the global field?
It is going to, no, I haven't tried, but I think it would actually make the torus stable zone smaller, because the field is going to be weaker, yes.
Because it'll decay faster, because it has a switch sign.
Yeah. So the argument is that you sort of expect that happening, and we argue that this is sort of the upper limit of what you would get. The same goes with the higher order of global field. If you get a quadrupole or octupole, the decrease would be faster as well. So.
We often use type 2 radio bursts in properties. Have the same properties. So how do you think on using such?
That's right. This actually mentioned here. People have done a few, I think, campaigns, tens of hour campaigns with VLT the arrays and tests. They've looked at tens of hours on a particular several targets, right? On one target. No, not at all. They've seen, I think, maybe a type 4 type stuff pattern, but no type 2. They've seen a few super flares on their star over the campaign, but no type 2. So one thing they argue that is maybe there is CME, but the CME is slow as shown by this diagram. The CME is below the sound speed, so you don't have a shock at all.
Yes, type 2 bursts are signatures of corona shocks or interplanetary shocks, but it's not necessary or sufficient condition for shocks. And of course, the slow CMEs won't drive a shock.
So another question? If not, let's thank Xudong again for the excellent